We move now to describe the simplest pursuit algorithm, the thresholding strategy. We already met several greedy algorithms and seen how they trade complexity for accuracy. On the complexity axis, this is the order of the methods introduced. We turn now to present a method called the thresholding algorithm. It is the simplest pursuit possible, and thus also the least accurate. Despite its crude treatment of our P0 problem, this method is very popular and highly effective in various scenarios. How could we simplify beyond the OMP and its variants? The thresholding algorithm does so by questioning the sequentiality of these methods of finding the support one element at a time. How do we choose our atoms? Whereas the least squares OMP is doing the best it can do in reducing the representation error, OMP is slightly simpler, relying on the residual. The thresholding algorithm considers both to be just too complicated. What is the alternative? Well, it is a process that hides in the very first step of the OMP, the computation of A transpose times B. The absolute value of this vector tells us a story about the involvement of all the atoms with respect to B. The bigger the inner product, the more pronounced this atom is in describing B. Here is a detailed description of the thresholding algorithm. We initialize it by computing A transpose B and taking the absolute value of this vector. We sort the entries of this vector from the largest down. This is the order of atoms we shall use in choosing the support. From here on, the algorithm proceeds as if it is the OMP. We start with an empty support and add one atom at a time from the above order, solving a least squares task per each step in order to evaluate the residual. The residual itself is used here only for the stopping condition. While the overall structure may seem similar to the OMP, the burden of choosing the next atom has been eased dramatically. While OMP requires M, N, K operations to complete a solution with K atoms, the thresholding algorithm uses only M times N operations, regardless of K. This, of course, is under the assumption that the least squares part is negligible. In this context, the recursive least squares method presented earlier can be used here in order to reduce this stage's complexity. And if you thought that this is the bottom of the road in terms of simplifications, here is another twist to the thresholding algorithm that may make it even cheaper. Imagine that A is of size 1 million rows by 10 million columns, and the support we are after includes 100,000 non-zeros. Are we really willing to solve a least squares problem with so many unknowns? In doing so, we may lose all the appeal of the thresholding method. A variant of the thresholding could be suggested, where the projection values taken from the vector A transpose B are considered as the crude approximation of the least squares solution. This should remind you of the matching pursuit strategy. By the way, if the atoms in the support are normalized and nearly orthogonal to each other, this approximation becomes quite exact. Do you know why? In case you are wondering who will ever make use of such a brutal method, surprisingly, it is quite effective in image processing and machine learning. Indeed, this simplified thresholding algorithm is the bread and butter behind most deep learning architectures.